Okay, so I believe last time we started talking about Chapter 1, Part A. I know we discussed the definition of anatomy and physiology, all right? We studied subdivisions of anatomy and physiology, and then we talked about this right here, this property, this principle about anatomy and physiology. Okay. Took a look at an example of that, and then we started talking about the levels of organization or structural organization of the body, right? So we started talking about these a little bit. We saw that example, right? That smooth muscle there, in fact, lining part of the blood vessel or a layer of the blood vessel, and when that contracts and relaxes, it actually opens and closes or retracts the actual, what we call the lumen, right? Or the opening where blood goes through. Blood pressure, in fact, works mainly through muscle. Okay? When you talk about responsiveness then, responsiveness is, quote unquote, the ability to sense, respond to a stimulus. Okay? So they sense something, that stimuli, and then they respond to it in some form or fashion. That response can be an aggravated response, can cause things to go up or increase, or that response can cause things to go down or decrease. Depends on what it is. And so this is another one that's really quite large. It's a gray area here because it can mean a lot of different things in the body. But in fact, this one's really important because we talk about environmental changes, right? When the environment on the outside of the body, or sometimes in the inside of the body, changes, our body has to adjust or respond to it, in fact, to continue that homeostasis, that theme I talked about in the syllabi, which we'll talk about here as well, right? Homeostasis. Digestion. Now, we commonly think of digestion in the human body as taking in food, stomach, esophagus, stomach, small intestine, large intestine, breaking the food down, bringing the food into your body or nutrients into your body, etc., etc. And that's true. But what we also talk about in digestion is actually moving those molecules that food is composed of and getting them into the cells so the cells will actually use them for work, right? So we love to talk about food and stomach, small intestine, that's digestion, but we forget commonly about the cellular, what it really means in the cellular level. Metabolism, right? Every living organism has some sort of metabolism, and what I like to think of metabolism is the sum or the total number of chemical reactions that are occurring in a body at one given time. Okay, so if it's humans, we can talk about this large metabolism, like the metabolism of your entire body, but you can also talk about cellular metabolism, how the cells are working to actually doing this, right? And we know that metabolism, we'll talk about this in chemistry, but we know that metabolism is composed of breaking down stuff and building stuff up. And those words we use catabolism and anabolism to describe those. And again, we're going to revisit this in the chemistry portion, chapter 2. But when we measure how many breaking down things and how many building up things, basically, in one given time, that's metabolism. Okay. Excretion, right? So this is different than secretion. This is excretion. Okay. This is, in fact, getting waste out of your body. And, in fact, it relates to metabolism because we actually create waste from metabolism. In the process of breaking down stuff and building stuff up, we, in fact, create side products that the body cannot use. And because that is the case, we get that out of our body in many different ways. One main way we do that is through urination, urine, and the component, most of the component of what is urine, we call that urea, comes from the breakdown of proteins in your body. So when your body utilizes proteins, the side product is what we call urea. You add it to water, it becomes urine. That's where that word comes from. I'll give you an example of another waste we call carbon dioxide, right? Written like that in chemistry, and we know that carbon dioxide specifically it can't really be used in the body per se, and we know that it builds up really, really quickly. We have a lot of it from metabolism, and because of that we need to get rid of it, and really that's the responsibility of the respiratory system. The respiratory system's responsibility is to take in oxygen, which many of us already know, right? But the other main important function is to blow out or expire carbon dioxide. And that's getting that particular waste out. And of course, feces. Feces has a lot of things, including undigested food we don't really actually use at the time. But also a lot of the other breakdown from metabolism gets taken in and taken out through feces. Reproduction. To consider yourself being a living organism, you must reproduce. Okay? Now this occurs in two main ways. At the small scale level in the cell, we talk about this, right? Mainly division of cells, right? Or mitosis, right? Mitosis. Now, we can do this if we want to make more cells, which, depending on the body system or the tissue, can happen. Or we can do this for repair, right? If the cells get damaged and we need to grow new ones because the other ones are damaged, we can do this in that regard. In the large scale, in the organism level, producing offspring, right? Carrying on your DNA from one person to the next person. And in fact, that's the number one goal of every living organism. Is to reproduce. Okay? From a pure science biological standpoint. I like to say that because there's always a subset of, you have to make an addendum to it because that doesn't include any type of ethics or morals or anything like that. It's just talking about pure biology, right? The goal of every living organism is to reproduce, bottom line. And because of that, living organisms and humans our body is invested in that process of creating the cells that contain the DNA, viable, all that process, the process of reproduction, all of that is invested. We spend a lot of energy, time, and effort in our body for that to happen, to become very successful with it. Okay, growth, right? Growth actually means an increase in size, right, of a body part or a tissue or a cell of an organism. That's what growth means. Okay. Okay, so those are the life conditions that need to be met, again, for a living organism. And again, this is just basics, right, for right now, basics. Okay? So let's talk about this, right? We know that humans are multicellular in regards of trillions with a T of cells in our body. Because those cells are considered living, those individual cells have all of those conditions met that we just talked about. They have to be kept alive. We have to keep them alive long enough for them to do their job, basically. I mean, that's as basic as it is, right? And that's why we've got organ systems in place. The organ systems actually service the cells of our body. Many times they're self-servicing. So the cells that do jobs to help other cells live are in fact doing those jobs to help themselves live. Does that make sense? And other body system organ systems are doing the same thing for those cells, and back and forth. Okay? All in the goal to survive or to keep living, so that way we can fulfill what? What's the number one goal again? Reproduction. Right? That's the goal. Okay? There are 11 organ systems. You will be responsible for knowing each 11. Okay? And knowing what organs fall in each organ system. Okay? I'll show you those, and you can find those in the book, because I have those on the PowerPoint as well. Okay? But before we get to that, figure 1.3 shows you a great example of how many organ systems work together here. Okay? We can see the digestive system working here to take nutrients, right? Water, because water is not really considered a, I mean, yeah, some people say it's a nutrient, some people say it's not. But those things get broken down and taken into the bloodstream. That's the cardiovascular system. And the cardiovascular system, responsibility for this, in this regard, is to take those nutrients and, like a highway, a taxi system, taking those nutrients and water and what have you to cells, right? You see these down at the bottom, right? Nutrients get dropped off, water gets dropped off, cells take it in, right? At the same time, there's an exchange, so the cells might say, okay, here's all my waste, here's all my garbage from doing my job, here it is. That goes into the bloodstream. One of the systems that is responsible for excretion, right, of waste is the urinary system, like urea and extra water and things like that. Go through the urinary system, excretion out the urinary system. The respiratory system is responsible for taking in oxygen, so that's already coming in, but also coming out carbon dioxide, which we said was a waste, right? And then finally, you can see the integumentary system, right? Is protecting everything. That big old kind of square around the whole thing is protecting everything. So we're actually seeing all those conditions of life, right? All kind of coming into play and seeing how the organ systems are helping each other overall, kind of helping everybody to continue life, right? And so the bottom line is for y'all is that as y'all become clinicians later on, hopefully you understand how all of this kind of works together, not completely, because that's a lot of studying, right? More than just this class. But if you understand a good amount of it, you understand when some of these places, some of these systems go wrong. Does that make sense? Sometimes when they go wrong, it throws everything out of whack, or homeostasis is in imbalance. And your job was going to be to kind of find out Why is it going wrong? And then what do we do to fix it, right? You should already understand what's gone wrong by assessing. But your main job is to do something, do some intervention, some therapy to get the person back to normal. That's really the whole bottom line. Okay, so here are all your body organ systems, right? These are found in the textbook. I decided to put them on the PowerPoint. But you'll notice that this is the integumentary system. You see that there are different sections of the integumentary system. That's what I want you to know. The 11 body systems. What each one of them, right? The skeletal, muscular, nervous. Okay, pretty self-explanatory, so that's why I'm not going in detail, but endocrine system, okay, cardiovascular system, lymphatic system, and we call what we used to call immune system, or now immunity, kind of fall one and the same, because the lymphatic system, in fact, is the highway system for the immune system cells to kind of migrate through, kind of put themselves in different parts of the body, right? So that's kind of where we see this kind of respiratory system. So anytime you hear bronchos, then you would know, okay, that's part of the respiratory system. Digestive. Of course. The urinary. And the reproductive system. That's the male side, of course. And then there's another for the female side. Okay? All right. So let's talk about survival needs really quick. Let's go through this. Many of this is self-explanatory, right? So I won't go into too much detail. And your book does a good job of explaining it. So far be it for me to explain more than what the book is really showing at this part. So I'll go somewhat fast with this, right? So here are the list here. Here is the list of things, needs that are crucial for survival, right? If we don't get these in some form or fashion, and it depends on how long that is, then bad things happen. We start to lose function, organ function. Those organs will fail, systems will fail, and then organism will fail, which means organism will die, right? Okay, so let's talk about nutrients, right? Nutrients actually are made up of chemicals, just like the body is as well. Nutrients, when we break them down, get used for energy. That's the number one. Function, right? We're talking about function now. And number two, to build the cell. Parts of the cell itself, the things that the cell uses, that's what chemicals get used. That's what nutrients get used for. Okay? Now we know that nutrients for the human body, and actually all living organisms, are broken down into really four areas, right? Carbs, carbohydrates, proteins, what we call lipids. I wish they had put lipids on here. Fats, right? Lipids. And then this one right here, vitamins and minerals are also really important, right? So again, if we don't get a good mix of all of these things, then the body then starts to act funny, right? Starts to be abnormal in its function. Oxygen is really important because we use it when we break down food and break down nutrients to harness the energy that we need, oxygen gets used in a major important step at the end of all that. Okay? And I don't want to go into too much detail about cellular respiration, but that's the process, main process of actually making the energy molecule that we need, and we call that ATP, right? Okay? In the process of making that energy molecule, or breaking down nutrients to release their energy so we can put it into this molecule, we need oxygen in that final step, basically. Okay? Now, you might think about ATP and that energy molecule and how the body uses that when we break this, we release the energy. Energy gets used in motion and work of the cell. And that when we don't have enough of this, then the cells will actually starve to death really quickly and they'll die. Does that make sense to you? Okay. Now, many students start to think, well, if we take away oxygen, we know that we can't live without oxygen, right? Cover your nose and your mouth for a while, then you start to, or get yourself under the water. And most people can last less than a minute, and then after that, you're dying for water or for oxygen. But why is that the case when we make this in the body? Why can't we just continue to make it and have energy? Well, the reason why is because we don't store this a lot in the body. We make it really quickly, but we don't have a really good way of storing it in the body or in the cells, if you will. And because we don't do that, we consistently need oxygen to consistently make this stuff, ATP. Does that make sense? The minute we take away oxygen, or the second we take away oxygen, is the second we start to lose these. These don't get made. It's like we turn off the faucet, basically. And then no energy gets made, cells begin to die. Water, right? Most abundant chemical in the body, we know that for sure. Close to 70% of our body is pure water. It's a tremendous amount of water for a living organism, right? Just us existing, that's a lot of water. We're made mostly of water, which is kind of a weird thing to think about. But this watery environment is perfect for a lot of things, including chemical reactions. And this environment is needed for those chemical reactions to occur, right? If we don't have this water area where the chemical reactions can occur, then those chemical reactions will not occur. We have to have somewhat of a balanced or average body temperature, right? And we know that temperature is 37 degrees Celsius or 98.6 degrees Fahrenheit. Since we're Americans, right? We like Fahrenheit versus Celsius. The rest of the world loves Celsius. We are the only ones that are Fahrenheit, right? But why do we keep that body temperature? We go back to chemical reactions. Those chemical reactions work the best in that middle 37 degrees Celsius range there. Now we can go up a little bit or down just a little bit and it'll still work okay. But after, let's say, 1 degree or 2, then things start to go awry. Absolutely. Go ahead.
It's weird to me because I have 2 kids whose temp is always like 97.6 all the time.
Really?
Unless they're sick.
Okay.
So is that bad?
No, it's not bad. Their body temperature is just lower. They've set their brain has set that temperature for a lower temperature, and that's not necessarily a bad thing. There's a big range, by the way. Yeah. We call this the average because it is an average, which means not everybody fits in the average. And people that are outside that average don't necessarily mean to say that's abnormal. They're outside the average. Yeah. Yeah. It's safer to be at that level than to say we're always at 100. That's totally different. Yeah, because higher temperatures are usually bad, worse things. The chemical reactions, the enzymes don't work well, and that could be an issue. Yeah, cells don't work. They don't like it in a higher temperature. Yeah, so it's totally fine. If they've been like that all the time, that's. So their body chemistry is set up for that temperature, and that's totally fine. Yeah.
I know that they're starting to get sick when they reach about 98.6.
For them, yeah, for them.
Because it's not normal for them.
Yeah, interesting. Yeah.
Yeah.
I've heard that before, so it's not like it's abnormal.
Yeah.
It's not like it's a
I mean,
rare
I have
thing.
multiple kids, but they're the only two that have
That are set at
that
that
are set
their
at
basal
So
temperature.
they're just so different from the rest of.
Wow, it's interesting. Interesting stuff. So let's talk about atmospheric pressure, right? So when we talk about atmospheric pressure, we're talking about the pressure outside of our body, right? This is the atmosphere, right? Basically, anything outside of our body. That pressure needs to be stabilized, right? And it needs to be just right for breathing and gas exchange in the lungs, right? So the respiratory system needs to have that pressure. Now, that pressure can drop and it can increase, and our body can adjust to that, and that's totally fine, but it does take a while for that to happen, okay? If you've ever gone to Denver, Colorado, it's a mile-high city. The reason why they call it mile-high is because it's mile-high above sea level, and that's way higher than where we're at sitting here, right? We're higher than sea level right now, but not by much. That's much, much higher. And if you ever go to Denver, you'll immediately feel the difference as you get off the plane and get in and walk around. And your body will adjust to that. And over time, you won't feel the labored breathing that you might feel, right? So, but that's in range also. Okay. So homeostasis, right? Homeostasis, right, is maintaining stable internal conditions, right? The whole goal is to actually maintain that internal stable conditions while everything else is changing, because everything else will change. And that's what we talk about when we talk about the environment. Now we use that word, many different ways, and many people, when they come in, they'll think environment like climate change, stuff like that. We use that word there, but when we're talking about using environment here is how things will change on the outside of the body, and sometimes in the inside of the body will change from second to second, minute to minute, and we're constantly adjusting our body for that. Now that has started since the get-go, right? As an infant all the way through, you're constantly adjusting that, if you will. Does that make sense to you? We're going to talk about some examples of that as well. But that's what we're doing, is constantly adjusting to it, right? Always readjusting as needed. Okay? Now, who's doing this? The organ systems. Every single organ system is responsible for maintaining homeostasis, and together they maintain homeostasis. Okay? Now, how do we do this? The body has to constantly search, read, monitor, okay, that information, and then adjust for that information, that stimulus, whether that be on the outside of the body, in our inside of the body, in our lungs, in our digestive system. It doesn't matter in any of those organ systems, okay? So who plays a major role? We actually have two organ systems that play a major role in maintaining homeostasis, although everybody else plays a role as well. The nervous system and the endocrine system. Those two play a major role, or major roles in maintaining this homeostasis. When we talk about homeostasis, we talk about variables, okay? Which is a term that we talk about in science, right? When you look about scientific experiments, what's a variable? But what a variable basically is things that can change, right? So if you think about things that can change, that are variables in homeostatic controls, we're talking about things that can change. Temperature, pressure. This is a great one right here. Blood sugar, right? We know that can change in the body. And because it changes in the body, we have to adjust to that blood sugar. Really quick, I want you to think of how this can go up and down. How can blood sugar go up and down? Give me some examples that you would think of if you're thinking about human body, sugar in blood, Why would that be going up and down? Why would that change? Why is that a variable?
The insulin, food.
So what about food? Expand on that one. What do you mean by food?
The types of food that you eat, the sugar, the not have enough.
Okay.
Go down, and then you can have too much or have diabetes.
Okay. Yeah, and so the type of food means a whole bunch. How much you eat and how much you don't eat. What's the other factor in food? Just talking about food. The type, and then how much you eat and don't eat, and then what else? The what? Time, right?
Right.
When you eat it,
Eating it before bed is the worst.
right? Doing that, exactly. When you eat it, how many times you eat it, right?
How much you eat it.
And then how much, and all of that, and the types, and all of that plays a role. Because when we break that stuff down, that adds to your blood sugar. Very good. Okay. What else beside food would factor into blood sugar being a variable? This is a little bit more challenging.
Like your physical activity?
Good. Very good. Yeah, your physical activity. All right? Now, what do you mean by that?
Like if you exercise or don't.
Okay, so if you exercise, if you don't exercise, if you keep active, if you don't keep active, right? If you have an active lifestyle, then you can talk about job, right? If you have a job that you sit down for, I don't know, 12 hours a day, that might not be using enough of the energy, and that can add to your blood sugar. Yeah, good. Anything else with blood sugar that can lead to it being a variable that you can think of? Exercise is a great one.
Environment you're in?
Well, that's a big scale. That's like I answered the question, but it's not. Yeah, yeah. But yeah, we're all talking about environment, right?
Would it be
What about-
diabetes?
Huh?
Be one of them? The types of diabetes that you could have.
So yeah, that can be one of them. But what does that mean to you? Like, expand on that. a
It's
little.
kind of more like a family history thing because that runs in my family on both sides.
Okay.
Because on my sister, she has a different father, and his is the opposite of what
Mhm.
my grandmother's is and my uncle's and everything. So it's like one has not enough and one has too much.
Too much. Yeah. So it's genetics, is what you're saying, right?
Yeah.
Genetics plays a big role. Yeah. Good. Good. Now, so I think what you mean by environment, hopefully, and you'll agree with me, or you'll just say like, yeah, that's what I meant, is environmental stressors, right? So stress actually plays a role in this blood sugar up and down, I think, because it's, as you get stressed or not get stressed, what actually occurs in the body is that your body will tell your cells, we need more sugar in blood because we need more energy because we're scared or we're stressed or we're doing this, and you got a flood of blood sugar, and your blood sugar will rise, right? The whole point being is every single thing adds to this. Does that make sense? And so you could take each one of these examples as you're studying to understand the big picture, like body temperature. What are the factors that are leading the body temperature? Well, that could be outside factors like it's hot outside, or it's humid like today and yesterday, or it's really cold, or we had a big freeze, which we don't in Uvalde, but you know what I'm saying, right? Those type of things add to that body temperature too, and so on and so forth. Okay. So in homeostasis, we've got three components or three main parts that are considered part of homeostasis, right? A receptor, a control center, and an effector. Okay? A receptor is also known as a sensor. A sensor is the one that monitors or senses the environment. And it will respond to a stimuli, right? Heat from the outside of from the sun is a stimulus, right? Hits the UV rays, and the heat itself hits our skin. There's receptors on our skin that sense that change in temperature, right? And their responsibility, the receptor's responsibility, is to send that signal to a place called the control center. Now, usually our control center is a special part of our body, and it falls under the nervous system. And where do you think that particular organ is, or what that particular organ is? It's the control center, mainly. Yeah, good. Right? That's your control center mainly. And there are parts of your brain, in fact, that, for example, will maintain certain set points, for example, body temperature, and that's those sensors are sending that signal up to the brain. And the brain's saying, okay, I get the sensation, I get the stimulus, I'm going to make sure it's right at the temperature it's supposed to be or set point it's supposed to be, and if it's not, I'm going to send signals out to adjust to that. Again, homeostasis, right? The control center receives the input from the receptor, and then it determines the response. What are they going to do about it? Right? That's the responsibility of the control center. And then the effector, it receives the output from the control center, and will respond to it. Okay? Now, if the response by the effector is going to decrease the stimulation, we call that a negative feedback, reduce or decrease, or in some cases increase the response, we call that positive feedback. Okay? Negative feedback is the most common one that we have in our body that's set up as an effector in our body. Okay? Most common one. This is the one that will reduce or shut off the original stimulus. Right? That's negative feedback. This is the variable changes that are opposite. So if something makes something go up, then the response is going to make it go what? Down. Right? Or something goes down, the opposite effects, the effector, is going to cause it to go up.
So why exactly is it called negative feedback if it does positive things?
Right, when it does positive things. So positive in the fact that it will add to things, but negative in the fact that it's going to change, right? It's going to do the opposite. So when we use positive feedback in science, it's like an on and off. It's like a 1 and a 0. And we use negative or the negative value as the off, on.
Right, okay.
Or the opposite, I would say. The opposite. Even though it does not always decrease. Sometimes it can increase. Or do the opposite, yeah. What you don't want is what you're going to see in positive feedback, as an example, is there's an increase of something, and that response causes a greater increase, and a greater increase, and a greater increase over time. Does that make sense? That's positive, 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 positive. That's what you see in positive feedback. And negative, it's always opposite. Okay? They give you some examples of these. Body temperature is a great one. Okay? And you can use this as an example. So when you're studying, I want to make sure that you understand you need to use examples. Talk through some of the examples because they help you with negative feedback. Okay? Homeostasis is known as a balancing beam or a seesaw. Everybody can see the seesaw there. The even seesaw, the balance, is homeostasis right there. The main goal of the body is to always keep it at this balancing seesaw, kind of even. In reality, it's never going to be even. Does that make sense? There's always going to be slight moving up and down. Always, 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 right? But if we can keep it somewhat stable, even like this, we're good. That should be normal functioning. The body should be at normal, its normal job, okay? Now, when we see these major ups like this and downs like this, those are different changes, absolutely extreme changes. And we have ways of getting it back to normal. So that could be fine. But sometimes the balancing beam stays at this level and doesn't move from there over time. And in that situation, in that regard, that is usually a sign of a disease. Does that make sense? When you see a disease, the balancing beam is usually stuck here or stuck the other way. It can be too low or too high, whatever it is, but it's stuck there. And your job as clinicians are to get that balancing beam back, to try to get it to here. Because sometimes the body's internal controls might not be there, or might be misfunctioning or not helping whatsoever. They're failing. So we have to do some kind of therapy, medication, whatever, to get them physically back. And that's sometimes where medication comes into play, because we're actually helping the body get this back to normal, medically or chemically. Does that make sense to everybody? That's why this is important. That's why we talk about it in homeostasis, and that's why it's here at the very beginning. Here's an example of body temperature, and here's the negative feedback system, right? And what we're seeing is two balancing beams, two circles. But this one is talking about when the body gets too cold and what happens as a response. And when the body gets too hot, what happens as a response. Okay? That's negative feedback there. Okay? All right. Let's talk about positive feedback, right? So very much, we got the original stimuli. We have an enhancement or an increased response or exaggeration of the response. So again, as we have a original stimulus will cause an increased stimulus, so that arrow extending means an increased stimulus. And that'll cause an increased stimulus, and so on and so forth. If you'll notice, my simple graph here, you'll see the trend moving up, right? You see that going higher and higher and higher, right? So it'll cause it to go higher and higher and higher. This is not as common in the body as a negative feedback system, but you see a great example of that there, right? Labor contractions. And that's why labor contractions, for example, get stronger, more intense, more frequent as you move along through time, right? Because the original pressure changing, fluid breaking response, that's the stimulus basically. Does that make sense? That stimulus sends a signal to the brain, okay? The brain will then release, in a female going through labor, oxytocin. That's a chemical, and that's actually a hormone from the endocrine system, goes and floods the bloodstream, gets to the actual muscles, the smooth muscle of the uterus, and then causes the smooth muscles of the uterus to then contract. That contraction sends another stimulus to the brain, releasing more oxytocin, and that cycle keeps going on until the contractions get stronger, 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 so strong that they're completely trying to, push out the child. Does that make sense? And that's what we see there. That's a positive feedback system. We also see this here when we have breaks in blood vessels, right? Platelets, which are part of the bloodstream, block the broken vessel, and then that causes even more platelets to come and attach themselves because there's more secretion of chemicals, so on and so on. Okay, and we see that there in figure 1.7. This is the positive feedback because there's chemical releases from the platelets, and that tells more platelets to come, secretes more chemicals, causes more platelets to come, secretes more chemicals, on and on until we see this. And eventually it'll stop. Does that make sense? The job is completed. It'll stop completely. Okay? And then that cycle will then stop completely because we've already done what we're supposed to do, right? This is an imbalance. Does that make sense? I just want you to understand that this could be the balancing beam here, right? That's gone because what has happened? Blood's leaking, right? Leaking out. So we're losing blood here, so that's the imbalance. And what are we trying to do? Get it back to blood not leaking out of the blood vessel. Okay? Again, I mentioned this, right? What happens when we mess with homeostasis? We continuously do it in an aggravated sense. It'll increase the risk of disease. But even at that, if your body's normal, aging also plays a role in disrupting homeostasis. So what I mean to say by that is that as the older you get, the more your homeostatic controls are less sensitive. They don't work as well. Okay? That's a problem, and that's a special way of looking at folks that are aging, because they'll have this condition where homeostasis is not as efficient as it once was. So that's why, for example, if you're taking care of an elderly patient, you want to make sure that they don't overheat, right? Because overheating can happen with them because their homeostatic control is not as well. Now, that doesn't mean that they have a disease, it's just they're old. Does that make sense? And the older you get, your homeostatic control will become less and less. So it's true on that end. It's also true at the beginning, right? Infants, newborns, their brain is not developed enough. Their receptors are not developed enough. Their homeostasis is not as efficient yet because they're still developing that. That's why little children can get overheated, etc., etc., as an example. Does that make sense?